In the past 4 videos, we have first seen how to use the provided bash script to do a fully automated procedure of MCTDH-X, including simulation, analysis, and visualization. Then, we use only the provided input files to perform 2 series of simulations. We have performed a parameter sweep and searched for the ground state among a group of excited states with similar energies. This time, we use the bash scripts as a guideline and do the simulations partially manually. After these 2 exercises, we are already familiar with the program. Next, we will try to do it in the third way. We will start from an empty folder and do everything from scratch. This includes the relaxation, propagation, and analysis. We will reproduce the results in figure 6G. So this is the figure 6G. Here we are simulating the dynamical behaviors of 6 fermions in a double well potential, where the barrier height is ramped up rapidly from 0 to 20 with 1 time unit. So now let's look at the input files. The input files of this related to this simulation is given in the folder Relax19 Prop21 Fig 6G2L. In this folder, we have 4 subfolders, including a Relax subfolder and 3 Prop subfolder. In the Relax folder, we are doing relaxations of 6 fermions in a harmonic trap, and this serves as the initial state for the following propagations. And then in these propagation subfolders, we are doing the propagations, but we are ramping up the barrier height of the double well potential in different time scales. And specifically, we are now trying to do it according to the propagation in panel G, where we are ramping up in within 1 time unit. So now, instead of using this provided bash script, now we are doing the whole thing from scratch. Now we start from a completely empty folder, and we create a subfolder for relaxation. And we do first of all, we copy the binary files by bin cp and the input files, the exemplary input files, using impcp. So now we have these analysis.inp and MCTDHX.inp are the 2 exemplary input files for the simulation and analysis. And we also have these 3 library and executable files for the simulation. Now we want to modify the input file MCTDHX.inp. In order to do this, we can refer to the supplementary material, and in the table S4 of the supplementary material, here are the input variables for the relaxations, which is in the simulation number 19, and also the propagations, which are shown in the simulation number 21 here. So now we modify our input file according to this list, number 19 of the in this table. So first of all, we want to choose the job type, which means that we want to choose whether it is a fermions or a bosons. Now we are doing simulations with fermions, and we are doing the simulations with 10 orbitals and 6 particles, 6 fermions. And the interaction strength is chosen as 2, and the job prefecture is -10 because we are doing relaxation. And then we are using guess equals to hand, which means that we want to use a randomly generated initial condition. And the next are the DVR group of the input files. So we want to specify that we are doing simulations in 1 dimension, and we want to divide it into 512 grids. And our simulation starts at x equals to -8 and end at x equals to +8. 10 time units is enough for our relaxation, and we want to write our output every 1 time unit. And because we are doing relaxations, we want to use integration time step equals to 0.1, and coefficient integrator equals to DAV. Furthermore, we want to write the ASCII files, which means the orbs.dat files and the coef.dat files. Now we want to specify the one-body potential. So it is we want to use a harmonic trap H01D with trapping frequency equals to 1. So we don't need to modify anything. Now we want to specify the interaction. We want to use the regularized Coulomb interaction, which we can specify by using interaction type equals to 4, and which interaction equals to r-mctdhb. And then the interaction parameter 1, we choose it to be 0.1, and parameter 2 equals to be 100. So now we have successfully modified our input files, and if you want, you can compare what we have modified, the input variables that we have modified, and compare it with these entries in the table for simulation number 19. After this, now we can save our changes, and now we can start our simulations. So after waiting for some time, we have finished our simulations, and you can see that the MCTDH-X has generated many files, and we have already introduced these files in the previous videos, but now we want to look at some of the results to make sure that we are doing the simulation correctly. So now let's look at the last line of the NOPR file. We can first look at the orbital occupations. So we can see that the occupation of the first 6 orbitals are roughly equal to 1/6. So if we are simulating non-interacting fermions, then because of the Pauli principle, they should be exactly 1/6. However, because now the fermions are interacting, they are slightly deviates from the 1/6. And then let's look at the energy, which is 36. If the fermions are non-interacting, then we can do the calculation. The energy should be equals to 1/2 plus 3/2 plus 5/2 plus 7/2 plus 9/2 plus 11/2. And the sum of these is equals to 18. So we can see that 36 is much larger than 18. So we can see that the energy from the interaction is pretty high. And next, we can also look at the density distribution in the real space, and we can see that there were 6 peaks, and so the reason that there were 6 peaks could come from there were 2 possible origins. The first one is because of the Pauli principle, and the second one is because the interaction between them is because of the interaction between the fermions, and both of these reasons contribute to these peaks. So after doing the relaxation, now we want to do the propagation. For this, we create a new folder called prop, and inside the prop, first we want to copy the input files from the relax. This is simply because we don't want to modify so many input variables, so we want to use it as a template. So now we want to modify the input files, and this we can do it according to simulation number 21 in this table in the supplementary material. And now we could start to do this. So first, because we are now we want to do the propagations, so we would like to for the job prefactor we use 0 minus 1 instead of -1 0, and then because now we want to use binary files as initial state instead of a random initial state, so we choose get equals to binary files, and then we here binary start time should be 10 because we have the relaxations that we used as the initial state. We were in that simulations we were doing a simulation time equals to 10. So here we want to use binary start time equals to 10. And the next thing we want to modify here, here is the DVR variables. Here everything should remain the same because we are using the same binary files from the relaxation. So we want to keep all these variables to be the same. And then it's the parameters for the integrator. Now we want to start at time equals to 0 and finish at time equals to 30. So in the table, in this table S4 we says that we want to use time equals to 100, but here we because we want to save some time, so we simply use time equals to 30. And then because we are doing relaxations, we want to use integrator step size equals to 0.01, and the coefficients integrator is we should choose MCS. And then is the potential. For the potential, we want to use H01D plus time-dependent Gauss. And as I showed you previously, so here the first one is the harmonic trapping frequency, and then this is parameter 2 is the center of the harmonic trap, and then the parameter 3 is the height of the barrier at the end of the ramping, and parameter 4 is the time of the ramping, so which is 1, and then 5 and 6 is the 5 is where the center of the harmonic of the barrier should be, and parameter 6 is the width of the Gaussian barrier. So this is this is our one-body potential, and in our one-body potential, we are ramping up the barrier of our double well potential within 1 time unit. And in the end, we do not want to change our interaction, so these variables remain the same. And now we can save our file. And most importantly, we want to copy the binary files from our relaxation, the binary files, and also the header file from our relaxation, because the relaxation results, our initial state is stored in these 3 files. And lastly, it's also important is that we want to do the bin cp to copy our executables, GCC files, and our library. What we should remember is that we should not do the imp cp, because if we do that now, we would overwrite our input files. So now we can already start our propagations. The propagation has already finished, and we have obtained some files from the propagation. These include the orbs.dat and coif.dat files, the binary files, and also the nopr.out files. And so in the nopr.out file, we can find the orbital occupations and the energy of the system as functions of time. Now let's look at these evolutions. So first of all, we would look at the orbital occupations of the 10 orbitals, which are in the 11th column to the 2nd column in the nopr.out file. So now let's look at it. We can see that our ramping time is equals to 1 time unit, but the orbital occupations are rather insensitive to this ramping. Then we would also like to look at the energies, and we can see that the energy increases rapidly at the beginning and then kept as a constant. To look at the details, we want to look at only the first 5 time units, and we can see that the energy increases exactly in the first time unit, and then it is kept as a constant after the first time unit, because our ramping time is equals to 1. So now already in the energies of the system, we can find the effect of the ramping. Of course, we would also like to look at the density distribution up in the final time of the propagations at time unit equals to 30. We can see that this is the density distribution in the real space, and we can see that there were 6 peaks in total and 3 peaks in each of the well. So which means that this is reflects the fact that we have 6 fermions in total and 3 fermions in each well, and because of the Pauli principles, each fermion is represented by 1 peak in the density distribution. So even here in the density distribution in the real space, we can not really see the fluctuations in the particles. in order to look at the fluctuations of the particles, we would like to do the analysis and obtain the density distribution in the momentum space and also in the correlation function. So we are doing it at the time unit equals to 30 and with time points equals to 1. We could, of course, also look at the evolution of the density distribution in the momentum space. In this case, we want to do the analysis from time equals to 0, from 0 to 30 with 31 time points. Now let's go back to 3031. And then we want to change the dilation equals to 10. This is the resolution in the momentum space. And then we set density x and density k equals to true. These are the flags for the density distribution in the real and momentum space. And then we also want to generate the correlation function in the real space. So we set correlations x equals to true. Now we can start to do our analysis. Now the analysis has also finished, and we plot the density distribution in the momentum space. Now we can already see that there are some significant fluctuations in the momentum space density distribution. If you are not convinced, I have also simulated the ground state at with a barrier height equals to 20. Because after ramping, our barrier height is equals to 20, if you still remember. So I'm also simulating the ground state with exactly the same potential. So now we can compare. On the left-hand side, this is the density distribution in the real space in a time-evolved state with a fast ramping in the barrier height with ramping time equals to 1. And on the right-hand side, this is the ground state, the density distribution in the momentum space of a ground state in exactly the same Hamiltonian, exactly the same one-body potential. So we can see that there is some significant differences between these two distributions, and especially here we can see that there are some significant fluctuations. So after looking at the density distribution, we might also want to look at the one-body correlation function. And the one-body correlation function is expressed in the x correlations.dat file by this expression. So we can see that we have obtained exactly the same figure in figure 6G, and we can see that the fluctuations in this correlation function is really high. And in comparison, we can look at the same one-body correlation in the ground state. And here we can see that indeed there is a very large difference. So this is the one-body correlation function in the time-evolved state, and this is the same quantity in the ground state. And you can see that, for example, in the off-diagonal term, here it is vanishing. So maybe we want to also set CB range equal from 0 to 1. Such that we are comparing exactly the same color scheme. So here in the off diagonal, it is we have vanishing one-body correlations between the two while in the ground state, but in the time-evolved state, this it is not vanishing and it is fluctuative. And also here in the diagonal term, in the ground state, we can clearly see these beautiful patterns related to the fermionic nature of the system. However, this beautiful pattern can already not be seen in the time-evolved state, and which is already replaced by the large fluctuations in here. So now we have now finished our simulations, and we have done the relaxations, we have done the propagations, and also analysis, and we are which is the complete procedure of doing the MCTDH-X, and we are doing this completely from scratch without any provided bash script or any provided input files. So this is a complete procedure. Thanks a lot for watching these videos.